in our new monthly colloquium of ANPA Physics Education Research Division. So we are very excited to welcome Justine Schaen. I don't know whether I pronounce correctly. Okay. So Justine works for NSF Noir Lab in the Communications, Education and Engagement Department as an education specialist. Her background is in earth science and education. Justine earned her Master's of Science in Science Education from Montana State University and was a middle school science teacher for 10 years. She served as a practicum teacher for college students interested in science education. Justine is also an active member of the American Astronomical Society, right, which degraded Pluto from major planet to dwarf planet in, I believe, in 2006, I believe. So AAS Education Committee and serves as an Arizona Science Teachers Association ambassador. So today, Justine will be presenting on NSF Noir Lab in Rubin Observatory classroom activities for data analysis and discovery. Also, I would like to remind our future programs to the audience. ANPA Winter Week on December 21st, 22nd, 2024. There are many other programs, including faculty searches on nonlinear process by Professor Doug Petke, who is the head of the department at WPI Physics Department. So with that, I would like to request Justine. Justine has already shared the slides, so I would like to request the presentation. Thank you so much.
Great, thank you. What a wonderful introduction. Also, thank you so much to ANPA for having me here. This was a very exciting opportunity, and I hope that our audience can take away something from this presentation today to either bring back to your practice, whether you're a classroom teacher, or to use for your own interests as well. So you know a little bit about myself now, but feel free to also introduce yourself to our audience. Please let us know, where are you located? Did you wake up really early this morning, or is it late at night for you? What is your current role? And if you teach, what do you teach and what grade levels do you work with? So feel free to type in chat if you have that ability to do so, and let us know who we have here today. Okay, so first off, what is NSF's Noir Lab? Some of you may have heard of Noir Lab before, or you might recognize some of the telescopes that we operate, but Noir Lab stands for the National Optical Infrared Research in Astronomy Laboratory. We are the U.S. Center for National Ground-Based Optical Astronomy. And so we have different sites for all of our centers. We operate in Arizona, Hawaii, and Chile. And I'm just going to do a quick overview of our programs, but it's good to know a little background on what Noir Lab is, because that just transcends into our education programs. So it lets you know where the data is coming from and what type of data it is. So we have Kitt Peak National Observatory. This is located in southern Arizona. It's home to about 24 different telescopes. We have optical infrared telescopes here and some radio telescopes as well. The land is leased from the Tohono O'odham Nation, and our goal is to establish a really great relationship with them and honor and respect the land that we are on. Kitt Peak National Observatory was established in 1958. So even though it is old, it is still doing cutting edge science. So two telescopes that I want to point out. There's this WIN telescope here. It's a 3.5 meter telescope, and it is known for detecting exoplanets with the NUID instrument. And NUID is an O'odham word to see. And then we have Mayall, which is on top of, it's like one of the tallest points of our mountain here. So this is a 4 meter telescope. And Mail is using an instrument called DESI, which is the Dark Energy Spectroscopic Instrument, and it is making the largest 3D map of the universe. So cutting edge science being done at this observatory, even though it was established in 1958. We have Sierra Tololo Inter-American Observatory. This one's in Chile. It is about 50 miles east of La Serena. And it's kind of like, it's like the sister of Peak National Observatory. So we have a suite of telescopes here of various sizes, also doing cutting edge science with the dark energy camera. So it's able to produce these beautiful images of these astronomical objects in space. Gemini International Observatory, you're going to notice a theme here. We have one in the northern hemisphere, Gemini North, and then we have Gemini South in the southern hemisphere. Hawaii, Chile, both great locations to be seeing for astronomy. So they're twin 8-meter telescopes. That gives us the full sky coverage, with one being in the northern hemisphere, one being in the southern hemisphere. And then they're also known for their adaptive optics systems. Adaptive optics, that's a way that we use to compensate for seeing through the atmosphere. So the atmosphere is what causing the twinkling. When we look at stars, we see a twinkle, and the adaptive optic systems remove the twinkling. So we can have those really high quality, high resolution images. Vera C. Rubin Observatory, I'm going to talk more about this one later. But just as a quick overview, this is also one of NOIR-LAB's programs. Right now, it's in construction in Chile. We're going to be beginning operations in 2025. We are really excited for this observatory to come online and the flood of data that it's going to produce. It is conducting the legacy survey of space and time. So you're going to see LSST everywhere. This is a 10-year survey where Rubin Observatory is going to be imaging the entire southern sky every 3 to 4 nights for 10 years. So every year we're going to be looking deeper and deeper and deeper into space. And it's going to just produce so much data and let us know the different types of objects in our solar system. It's going to be able to tell us more about dark energy and dark matter, etc. So we are really excited for this up and coming observatory, and I'll talk more about this in just a little bit. And then we have the Community Science and Data Center. This is like our data hub. So I just mentioned 4 programs. Those programs are all observatories. And what do we do with all this data that's coming in? We need a place for it to go, and we want to help astronomers through their research cycle process, help them with time allocation, and develop the software that they need to access data. So that's what the Community Science and Data Center is. And so the mission of NOIR-LAB is then to use these facilities to provide data products and services for a diverse and inclusive community. And that's not only the astronomers, but it's also for educators and their classrooms and our local communities as well. And that's where my role comes in as an education specialist, to help take the data and services from these observatories and provide access to them for educators and students, and help them make sense of what we have for data. So I'm going to talk about 2 programs. One of them is the Teen Astronomy Cafe to Go program, and then another one aligns with Vera C. Rubin Observatory. So this first program, it originated as an in-person, like, extracurricular activity for high school students. And it started in 2017. Students would come to NOIR-LAB, local students would come to NOIR-LAB, and this was done all over the United States. And astronomers would give a talk about their research, and then students would get hands-on or start to explore data that aligned with the astronomers' research. Well, then the pandemic happened, and we couldn't meet in person anymore. So it evolved into a digital version where we would host our teen astronomy cafes on Zoom. The astronomers would give their lecture. They would also provide a Python notebook for students to explore an astronomical concept. And then we were left with these great resources and they were just sitting on our computers. So we wanted to put them out for teachers to use to bring into their classrooms. So that's where my role came in. I helped to create some educator guides for these activities and develop them into a nice package that a teacher can break down and choose different components of and use that with their students. So what's nice about these Python notebooks is that they're at the very basic level. You don't have to know any coding. The teacher does not need to know any coding. You can get through your entire lesson without knowing any coding. So it's a really great place to start when you want to introduce Python notebooks and what this tool is. And astronomers use Python notebooks to help them make sense of data. So let's have students do that. Let's bring it into our classrooms and have students get messy with data. What's great is that a Python notebook, you can just reset it. So you can make as many mistakes as you want. You can play around with it. You can do some modeling and you can restart, or if you make a mistake, it's no big deal. So that's one of the great things about this program. It is free. Right now, we have almost 7 packages ready to go. So they cover black holes, black hole orbits, both great for physics concepts, same with breaking the solar system, exoplanet atmospheres, gravitational lensing, backyard worlds, where we learn more about brown dwarfs. And then the one that is going to be online very soon is the large scale structure of the universe. So these packages all come with materials to support the educator. And I should add, even though Teen Astronomy Cafe was used with high school students, they're still great to use in the college classroom, especially at the 100 levels where you're starting to introduce these basic concepts to them and you're working with students that have no idea what a Python notebook is, or they're just at the beginning of learning coding. So these notebooks all come with the speaker slides, so the astronomer slides and their video. So as the teacher, if you wanted to, you could watch the video to get your own background in what the concept is, or you could assign it to your students to view the video before class or as homework. And then you have the slides as well. So if you didn't want the students to be viewing the video, you can present the slides. You can put your own slides into it. So you can make it your own as well. We have then the Python notebook activity, which has to do with whatever the presentation was from the astronomer. And then we have the teacher guide and student worksheet. The teacher guide, we've put in there which standards it supports using the next generation science standards. A lot of our states use some version of the next generation science standards, if not the NGSS. And then we've also identified, like for each activity in the notebook, some common questions that may come up or background knowledge that you should be aware of as you're doing each of the activities in the Python notebook with your students. And then we have a student worksheet. So if you want students to be writing down some of their thoughts or answering their questions as they go through the notebook on a piece of paper, you can print out the student worksheet, or you can assign it to them through your learning management system. So all of these materials are available online. I'm going to put this link in chat for you. It's on our Noir Lab website under education. You can check out our education programs, and this one is Teen Astronomy Cafe to Go, where you can access all of these activities and their educator resources. I just want to highlight a couple of these activities. I'm going to highlight breaking the solar system and our most recent one, brown dwarfs, just so you have an idea of what they look like and the different components to these packages. So breaking the solar system is introducing students to the stability of our solar system. So we first want to start by asking students, like, how stable is our solar system? They're going to start with like a very basic understanding. They might start to ask questions here, and this is what you're going to use to drive the learning. And you can connect back to this question after you've done the Python notebook and see how their understanding has evolved as they've done the activity. We provide them with a student worksheet that is going to introduce them to these different orbital parameters. for breaking the solar system. In one of the very first activities, they're making sense of Newton's laws of gravity, and specifically they're trying to understand how the different simulations are n-body simulations. So you can bring in the different laws, you can introduce that to your students, and then in the very first activity, they can just see a basic gravitational interaction between a hot Jupiter. So a hot Jupiter, they are gas giant exoplanets. They have relatively short orbital periods. It's thought that hot Jupiters start to form further out in their system and then migrate inwards, which is what's making them hot as they get closer to the sun. So they can start by thinking about other planetary systems in this activity. They can compare their exoplanet's orbit to another exoplanet's orbit to their neighbors, etc. So it's just a very basic way to get started in this notebook. And then we have them put in the orbital parameters of the solar system planets, and then they can see those interactions. And what they then need to do is try to break the solar system. So in the final activity, they're going to work in groups. They're going to use collaborative thinking, critical thinking to try to figure out, okay, which parameters can we change of the planets to try to break the stability of the solar system. And there's a lot of trial and error there, but they start by coming up with their own investigation plan, and then they work together to try to see if they can break the solar system. This on the right here is just a snapshot of one example of how you could break the solar system over time. And what I did here is I changed the inclination of Jupiter to be 90 degrees. So that orbit is very different than what it was before. And then you can see what's going to happen. Saturn has a catastrophic instability detected at 630,000 years. So that's one of my favorite notebook activities. And then in our backyard worlds brown dwarf activity, they start in the notebook by understanding, okay, what are brown dwarfs? And these are objects that they don't give off a lot of light, so they need to be detected using infrared. So data for the brown dwarfs notebook is coming from the WISE telescope, the WISE Space Telescope. And students, by the end of that notebook, can detect or identify brown dwarfs in these little movie clips. So then they practice their ability to identify brown dwarfs, and then we want them to actually apply it as citizen scientists. So then they go to Zooniverse and they check out Backyard Worlds Planet 9, and they start to be citizen scientists by identifying brown dwarfs. So we've given them all the practice, background understanding, and skills that they need to participate now in a citizen science project. Ooh. Okay, so that leads me to the next education program that I want to go over. I am going to start to talk about Rubin education. So at Noir Lab, most of my role is supporting our Noir Lab programs, and one of those is Rubin Observatory, and I work 25% with the Rubin EPO team to help create these online investigations. But first, I want to introduce this really unique observatory. So Veracity Rubin Observatory is in construction in Chile on Cerro Pachón. And again, Chile is a great place for these observatories. We expect first light to be occurring in mid-2025. And what's unique about this telescope is that it's designed for speed. It's designed to be really quick. You're imaging the entire southern sky every 3 to 4 nights. So you have to make sure that the telescope can move pretty quickly. So this is just a quick little video clip of how fast it actually can move and rotate on the mount. It has also a really unique mirror design. So if you want the telescope to move quickly, the mirrors can't be too heavy. It can't weigh it down too much. So they combined the M1 and M3 mirror. So the primary and tertiary mirror are combined into one mirror. The tertiary mirror concaves in a little bit. So it's lightweight, and they both the M1 and M3 use adaptive optics to compensate for the distortion caused by our atmosphere. So it's a really unique design. The other really amazing feature of Rubin Observatory is the LSST camera. So just remember, LSST stands for the Legacy Survey of Space and Time. So that's a survey it's doing over time. And this camera was built and funded by the US Department of Energy at SLAC National Accelerator Laboratory in Menlo Park, California. It's about the size of a compact car. It weighs about 3,200 pounds, and it uses 6 filters to image the sky. So each of these filters are assigned a wavelength from ultraviolet to infrared, and it's just going to help us look at different science in these images. I have a video. I'm not going to play the whole video for sake of time, but this camera arrived at the site. It's really cool to see the process of this camera going from California down to Chile, and it arrived at the site this year. So we've just been celebrating a lot of these major milestones this year as we're getting closer and closer to first light, or first look, as we're calling it with Rubin. So I'm going to play this. I'm not sure if the audio is going to be a little wonky. Let me see, share computer audio. Okay. I'll try. But the idea is that you can see like how much hard work went into this. Okay, so hopefully you can like just see how much hard work went into creating that camera. I know it might have been a little glitchy with me presenting it on my screen, but if you follow Pharisee Rubin Observatory through social media channels, a lot of those videos are being posted, and they're just so amazing to look at. Those videos are also available on our website too. But it's just these major milestones are being reached. The Rubin EPO team right now, so my colleague Artist Harold, who is like the education program is like her baby. She's in Chile right now for the very first time at this observatory, and the whole team is there as well. And it's just a major event for them. So I'm presenting on their behalf about all of their hard work that they have done. So you can see how passionate we all are about this observatory, and as we're getting closer to it being online, and how it's going to just revolutionize our understanding of the universe with 60 petabytes of raw image data. Holy smokes. So every single night, we are expecting about 20 terabytes of data. Just to give you an idea, like what is 20 terabytes of data, you can think it would take about 40 MacBooks to store 1 night's worth of data. That's also equivalent to more than 3 years of streaming video or 50 years of streaming music. And by the entire end of the survey, we're going to have 60 petabytes of raw image data or over 5 million images. And within that first week of operation, the camera will generate more data than the sum of all data collected by the Hubble Space Telescope. These images they're extremely wide, they go very deep, they cover about an area, like one image covers about the area of 40 full moons. So it's just an incredible amount of data, and we want to bring that into our education program. With all that data, we are going to identify 20 billion galaxies, 17 billion stars, 10 million supernovae, 6 million solar system objects, and so much more. And the main science goals, I've mentioned some of these before, like cataloging our solar system, the different objects that we'll detect in our solar system. So the observatory is not only going to look deep, but also close to home. And it will explore the transient sky, so like supernovae. We are going to hopefully understand more about the evolution and history of the Milky Way galaxy, and then also dark matter and dark energy. So the observatory was named after Vera C. Rubin, who is the astronomer who helped discover dark matter. So of course, that's one of the science goals. So this leads us into our education program. So all of that unique information about Rubin Observatory, we want to bring into the education program. So we want to serve our audience in a similar way. So we want our audience, we want to reach a wide audience. We want to reach all learners, just like the telescope's going to have wide images. We want everything to be fast. So the telescope can move quickly. We want teachers to be able to access the information, the lessons, quick, and just drop in the lessons where they need them to be. And then deep. So we are going to be looking deeper and deeper and deeper into space and time with Rubin Observatory. And then with our education program, we want students to be engaging with learning that is relevant and understandable to them. So there are 7 investigations available to students and teachers. They cover common topics that you would likely be teaching in an astronomy course at the high school level, or introduction to college level, or introduction to astronomy at the college level. There are middle school teachers that have used these as well in their classrooms, so it depends upon the background of your students. So that's our audience. And then these materials or the investigations, there's nothing to buy, there's nothing to prepare. You don't have to install anything on your computer. Everything is online. They're standalone lessons, so they can be done in about 2 hours or less. But we also have a lot of components that you can use to extend the learning. So you could just do the 2-hour lesson with your students, the 2-hour investigation, or you can use all the other support materials that we provide for you to bring out the learning to be longer, to be more like a week-long unit. All of the materials are available in English and Spanish, and it is free. I am going to put the link right now in chat, so if you wanted to explore these resources, you can do that as well. Okay, so these were designed for student engagement, successful student engagement. So there's a lot of interactive tools that can just introduce concepts, but also we have interactive tools to work with the data. We have many different ways that we're working with data. So it could be from histograms to visualizing data with an orbit viewer to working with light curves. So it's all interactive. We want students to be active learners. We want them to be also collaborative learners. So we are paralleling the authentic science process. So having them start to ask questions, they write down in every investigation where their initial thought process is at. And then by the end of the investigation, they can reflect back on their original thinking and see how that's changed over time. We have opportunities as well for them to use guided practice. So before just throwing the data at them to try to understand, we walk them through some examples too and give them feedback in if they're on the right path or if they need to look at what they're doing again. All the investigations use authentic data. So how does that work? Ruben's not collecting data yet. So what we've done, the astronomer on the Ruben EPO team has helped us find the most Ruben-like or Ruben-y data from other surveys and other telescopes. And we're using that data right now. And the idea is that when Ruben's online, we're just going to filter Ruben data into it as seamlessly as possible. So we have designed these investigations to support our novice learners. We want to attend to a wide range of cognitive abilities and cultural funds of knowledge. We want to guide students in effectively constructing their questions and interrogating the data. So that includes these tools to introduce the concepts and they're typically, the introduction components are typically at the beginning of the investigations. So then they're prepared to look at data and analyze data towards the end of the investigation. It engages students in reading comprehension and critical thinking, and then it helps to build their confidence in their ability to be successful at math or science. They don't have to worry too much if they're right about the math and if they're doing the equations the right way. We have these built-in tools and calculators to help them through that process and to start just making sense of the data. So when these investigations were first created and designed, this was before the pandemic, and we were ready to do pilot testing and user testing, and then the pandemic happened. So we started to test these in a virtual environment, and they just worked beautifully. So at the time, there was a lot of burnout from students just watching videos and doing worksheets. And so this just came at the perfect time for teachers. This was really in demand. Students could do the investigation, and then the teachers were looking for ways to facilitate still that collaborative learning. And we gave them some tools to do that. They could use breakout rooms if they were in a live Zoom format, or if they were just in their management system, they could start a chat thread or group conversations that way, open up office hours as well. So these investigations are designed to support the next generation science standards, but also Ruben is located in Chile, so we want them to support the Chilean Curriculum Nacional. They're set up very similar in the next generation science standards, use 3 dimensions for their standards, and same with the Chilean Curriculum Nacional. So we've outlined in all these investigations which standards they support, and then we also provide, like if you're wondering, okay, I want a quick idea of how students are going to be using all 3 dimensions of these standards in the lesson, they can see our lesson summarizer, which is also color-coded to match with the different components of the standards. Also, for my physics teachers out there who are tasked with also teaching earth and space science, my colleague Artis has created this wonderful document for you, which I recommend you make a copy of. So I'm going to put this in chat. This is just a spreadsheet where you can break down whether you teach the next, with the next generation science standards or not. You can just look at the physics topic column and you can filter that way. You can say, okay, I'm teaching about gravitation. Which of these Ruben investigations will support that? So you can filter that way as well, or you can filter by investigation too. So that's a wonderful research for my physics teachers. So the investigations, I mentioned this before, they come with a lot of support materials. You can use the pre-test and post-test to gauge student understanding. You can also use that to measure norms. It's just a quick 10-question multiple choice test. We provide you with an answer key for that as well. We have a phenomenon activity. So This is really like an engagement activity to have students start to build curiosity about the concept that's covered in the investigation. We have formative assessment questions. We want to make sure that students are understanding what's going on in the investigation. And then we also have a summative assessment that you can use after students have done the investigation. Maybe they were working in groups doing the online investigation and you want to get individual scores. You can open up our summative assessment question and assign that individually to students. So just one example of a phenomenon activity for our surveying the solar system investigation, students are looking at this video. It's a video, I just quickly took some snapshots here. It's a video on YouTube that shows asteroid discovery from 1970 to about, I think, 2015. And so they can see how how many asteroids have been discovered over time. And we want them to start to ask questions like, what do you see here? What do you notice? What are you left wondering about? So after students have watched this 5-minute video, a lot of them can pick up, okay, the yellow dot is the sun. And I see 1, 2, 3, 4, 5 blue dots. I think those are some planets. They can maybe even name those planets. They know by the title of the video that these things being discovered are asteroids, but what are these different colors? We have a green band, we have a yellowy orangey band, and we have a red band. And so we use this to drive the student thinking for surveying the solar system. So when they're in surveying the solar system, they start by looking at data with histograms of the different groups of small solar system objects. They look at their orbital parameters. And then after they get familiar with the orbital parameters of our solar system objects, they then look at the data a little differently. They look at it visually through our orbit viewer, and they're able to see these properties of solar system objects. And finally, then they are challenged to evaluate a new class of objects. And this can very likely happen with Rubin, with cataloging our solar system. We could find a brand new group of object or type of object. Does it fit into the other groups of object? And we have students do some modeling work and evaluating work to try to figure out this new class of objects. Okay, then I want to introduce Coloring the Universe. This is the last investigation I wanted to cover with you. What's great about this investigation for the physics teachers is it introduces the electromagnetic radiation. They're looking at different wavelengths of light, and specifically for Rubin Observatory, the filters and what wavelengths are passing through those filters. It's just a nice way to visualize different wavelengths. And then they are tasked with using 3 different filters. So Rubin's going to have 6, but we start them off small. We say, okay, let's first understand how to use filters to communicate information with just using 3. So they use U, I, and Z as the filters. That we teach them how to assign a color to each of the filter. So first they know that the image appears in grayscale, and then we assign the color to them. So this is also great for the physicists out there for teaching information technology and how we communicate information too. And then they get to adjust the color intensity just as our astronomers would. And what they're trying to do specifically in this activity is to create a color balanced image of a galaxy showing the star forming regions. And we give them a lot of background information on that too. It's not like they can just suddenly do that. And then their last activity is they get to choose their own astronomical object to try to investigate and to communicate some type of scientific information on. So at this point, yes, they've been introduced to star forming regions, but they've also been introduced to other science cases such as detecting faraway galaxies and redshift. So with that, I just wanted to take 1 minute real quick to show you Rubin Observatory and all of our other education resources, if that's okay, real quick. We have RubinObservatory.org. I'll put this link in chat. And we have so many different resources. You can click on Explore to find some fun facts. You can find profiles under Rubin Voices of the different people that work for Rubin Observatory, what their backgrounds are. You can hear about their profiles and how they got to where they are today. In Gallery, we have slideshows that can help you introduce concepts to your students, such as what is a survey telescope? And then in education, this is where you're going to want to go. If you are a teacher, you can click on educators and you can find information such as our program guide. You can learn more about each of the investigations, which all come with a teacher guide, common student questions as well. And then we also provide professional development for teachers. We have an upcoming session, I believe December 5th, with the American Modeling Teachers Association, and to focus on astronomy modeling. You can check out our events as well. So that's all under education in the educator tab. Also, I want to invite you to join our community of practice. So especially if you are an educator, stay up to date with what we have going on with Rubin Education. So our Facebook group is called Rubin Observatory Educators. You can feel free to engage with us there, post any questions that you have there as well. And then finally, thank you so much for having me. I want to leave the rest of the time open for any questions that you have. If you want me to elaborate more on any of our programs, I'm happy to do that too. And Dhanyabad.
Oh, thank you so much, Justine, for a great presentation. And I love your dhanyavad, like so you Nepali word. Thank you so much. So if you any of you have question, please ask the speaker. And let me start with, by the way, the Rubin Vera Observatory, is it located in the same spot as Alma in Chile, or in a different spot?
You know what? I'm not exactly sure of the exact location of Alma, but I'm assuming they're very close. Somebody here might know that answer. It's located in the Atacama Desert. These are great
yeah,
places.
exactly.
Yeah.
Yeah, that is the same.
Okay. Same area.
That is the same place.
Yeah.
Yeah, because I teach. I've never been to there, but I teach astrophysics courses, and one chapter is like all about these radio telescopes and adaptive optics. And actually, while we were presenting, I connected everything like to my class. Actually, thank you so much. And yeah, thank you again. So if there are any questions, please feel free to ask, unmute, and ask the speaker. Thank you.
While you're thinking of questions, I'll also put in chat our education and engagement newsletter. This is for anyone in our communities, whether you're an educator or not, and you're just interested in knowing what we have going on at our different sites or online opportunities for you to engage with us. I recommend you subscribe and stay up to date. We have a monthly newsletter that goes out. So I just put that link in chat as well.
Okay, great. A quick question, like while we are waiting for other questions, like, so anyone who is not in that geographical region also can use all these materials for free. Am I right? Like, for example, in Nepal, right? So we have our goal is to connect with the Nepali community, right? So in Nepal or elsewhere, so they can create an account for free in website, and they can get these materials, right?
That is right. So I will also show you, so everything's free. Anybody from anywhere can access these investigations. I am also going to show you one trick. So say you are teaching in Nepal and your students don't know English, or anywhere, like say you're teaching anywhere and your students, English is not their first language. We have English and Spanish available. Some of them also have the opportunity to go into French, but if you're using Google Chrome, if you right click, you can translate the selection and you can choose which language you want to translate it to. Let's see if I can find Nepali. Okay. We'll see. You guys can tell me how this turns out.
Wow.
Yes.
Wow.
So typically the translation works pretty well. If things start to look weird, you might want to go back to the English version to compare, but we've heard that Google Translate works fine for most people.
Fantastic.
Mhm.
Thank you.
Yeah.
Yeah. Any other question? Any questions from the audience?
While waiting for other questions, let me ask you one. So we got a answer key for the expanding universe, and right now you are busy on first slide. I understand that part. Is there any plan to create answer key for other investigations?
Yes, so we get emails quite often, and in most of our professional development sessions, it's the question that pops up. Is there an answer key? I think it's mostly for the educator just to feel validated and help save them maybe a little bit of time on their end, so they're not just wondering like what's going on here. So originally we weren't providing answer keys. We wanted to be more like the nature of science. There's a lot of random questions or a lot of randomized data in there. So not all students are working with the same data, but they're still trying to understand the same concepts. So creating an answer key got a little difficult. But because the demand is so high, we are working, it's a little slow now, but we are working to create an answer key for every investigation. And as Dr. Sagar Padal noticed, we posted it first in our community practice just to get feedback. Is this a welcome resource? And if we got a lot of positive feedback, yes. So we are working now to create answer keys for all of them. And we'll have those available for teachers. For all of the assessments that we have for Rubin investigations, you can only access the assessments and the answer keys to those assessments if you're logged in as an educator. And myself and my colleague artists were the ones who make sure you're actually an educator, not just a student trying to get into the answer keys.
Yeah, thank you. Great. One more question, like the Python notebooks, they are same as the Jupyter notebooks, or they are different?
Sorry, which notebook did you say first?
You showed the Python notebooks, like, so they are Jupyter notebooks, or they are different kind?
Yeah, they're Jupyter notebooks. They're hosted in Google Colab. So that's just the one thing to be aware of. If you go to open up those Teen Astronomy Cafe to Go notebooks, if your school is blocking access to Google Colab, then your students will likely have trouble accessing the activity. So work around with your IT department to allow that to go through.
Okay, thank you.
Mm-hmm.